Hey y'all, this is 2017 number 1, AP Physics. Excuse me. We've got an Atwoods machine. We've seen that before. And they have it set up like this. We've got M1 and M2. And they tell us in the directions, if we read carefully, M2 is always greater than M1. So that means this will accelerate down, and this one's going to accelerate up. First thing that we need to do is make force diagrams for these. For M1 and for M2. You've got a nice little grid to do that on. So on M1, let's see, there's the tension force up and gravity down. Now which one of those would be winning? Well, block 1 is going to accelerate upward, so that means that the tension will be winning. On block 2, the gravitational force on block 2 is going to be winning because it's going to accelerate down. But the tension forces are equal. They said that it is a frictionless pulley of negligible mass, so that means the tensions are the same. And they put this on a little grid, and one of the things they're going to look for here is that you recognize that those tension forces are the same. Because they put it on a nice little grid, it's not enough just to do this. That's nice and everything, but they put it on a little grid, so you need to make them look the same. Maybe we should make that a little longer. Make sure we recognize that it's bigger than T. So that's what we're looking for there. You can check out the scoring guide to see exactly how they scored that. B. Using the forces in your diagrams above, write an equation applying Newton's second law to each block and use those equations to derive. So they're giving us the end result that we're looking for. This is exactly what we did when we looked at the Atwoods machine. So here for block 1, I have tension winning, so it would be T minus M1G. And for block 2, that force on block 2 is going to be winners minus losers. And that's going to be M1A. That force is equal to mass times acceleration, don't you know? And every time we ever did this kind of problem in this would be one of the simpler examples, but even when we got to problems where the mass of the pulley was not negligible, we always ended up adding the equations that we got from Newton's second law. And if the pulley did have mass, would have a third one for the pulley. It'd be Newton's second law in rotational form, the net torque on the pulley. But always things will simplify that if you add their equations together, whether there's just two of them like here or more, and all of the tension forces will cancel out. So I'm going to do that. Oops, I put a G there, that should be an A. Let's fix that. So adding the two equations together, left-hand sides, I get M1A plus M2A. Adding these sides together, plus T minus T, those cancel out. I have M2G minus M1G. I'm trying to solve this for A, so I can factor an A out and then divide by M1 plus M2. And I can also factor a G out, especially even if you didn't think to do that, they have it in the form that they want us to get. So there it is. Great. All right. Now, they have a table here. So they tried this experiment with various different M2s and M1s. You might notice that the M2s are in fact always greater than M1. And in part C, they want us to indicate what quantities we could graph so that would get a straight line and we could use the slope to figure out what g was. Well, if I graph this as my y, vertical axis, and this as my x, then the slope of that line will actually just be g. Sometimes we graph a line and the slope is some other like combination of constants, and we have to like tease out the value we're interested in. But here, if I graph a on the vertical axis and m2 minus m1 over m1 plus m2 on the horizontal, then I'll get g as the slope. So on the vertical axis, I would like to graph a, and on the horizontal, I would like to graph this, m2 minus m1 over m1 plus m2. There's more than one way to do this, including if you switch these, your slope would just be g upside down, be 1 over g. You could distribute this or multiply this up to the other side and graph m1 plus m2 times a, and there's other ways of doing that, and those are all acceptable, but I think this is the most straightforward one. So in the table up above there, I would need to add the column, this column here, of m2 minus m1 over m1 plus m2. And I'll go ahead and just do that real quick. So let's see, for the first entry, m2 minus m1 would be 1, and if you add them together, that's 3, so it would be 1/3. What would the units be for this table here? Well, I've got a mass divided by a mass. So you could call it kilograms over kilograms, I suppose, if you want to, but it's actually a dimensional, it's just a ratio of masses, so there are no units for this. You could call it kilograms over kilograms, if that makes you happier. This one would be 1/5. This one would be 7/17. You can give the decimal values of these if you like. This one would be 2/14 or 1/7. Hope I'm just doing these in my head, so I hope I don't make any mistakes starting off here. And then 10, 14 would be a 4/28. Is that also, sorry, 4/24, 1/6. And you can graph those all. Probably to graph them, you would want to have them in decimal form. So 0.33, 0.20, whatever 7/17 is, and 0.14 and 0.17, and 7/17 is 0.41. So just a word about scaling. They this is going to be our horizontal axis. So it looks like the biggest one is 0.41. So if I make the axis go like 0.1, 0.2, 0.3, 0.4, and up to 0.5, that should fit pretty nicely. And my accelerations on the vertical axis, I also have 5 different boxes for that. And also the biggest one is in the 4s. So I think we could just number it up. So here on this axis we have m2 minus m1 over m1 plus m2. There are no units, it's dimensionless. And on this axis we have acceleration, measured in meters per second squared. And on this axis, it's not the only way to scale this, but I think it's certainly the easiest and most obvious. 3, 4, and 5 there. So you plot some points and should get some semblance of a straight line there. I'm going to go ahead and find the slope of that with my calculator. You're going to use 2 points on your best fit line and show that slope calculation. Let's see, so I go to Stat, Edit, and enter these values, 0.33, 0.2, 0.41, 0.14, 0.17. And over here, go up to L2. The way to clear out a list, we hit clear, not delete. You don't want to delete the list. Clear and then enter. And here we have, what are my accelerations? 3.02, just reading them out of the table, 1.82, 4.21, 1.15, 1.71. And we'll go to stat again and calculate number 4, our linear regression, and get, this is part D now, so you plotted them, I didn't actually plot them, and looks like the equation for my line, it's got a pretty small intercept, so I'm going to just let that be equal to 0. I'm not going to call it y's and x's. Let me just see what the directions say exactly. Using your straight line, determine an experimental value for g. So I would just say that the slope of this line is equal to 10.6. Units of slope would be meters per second squared over nothing, over dimensionless, so that slope is equal to g. So our experimental value is about 10.6, and you might get different results depending on exactly what points you used there. And part E, now they made this into what we call a half Atwoods machine. The experiment's now repeated, and like this, for the same values of M1 and M2, is the magnitude of the tension in the string when the blocks are moving higher, lower, or equal to the magnitude of the tension in the string when the blocks are moving in the first experiment. So there's different ways to do this. You could reason through it, maybe something like this. Now that we have this block is up on the top, we don't have the gravitational force on the first block is not involved in the net force on the system. Like once we have the tensions cancel out, the net force here is this minus this. The tensions cancel out. And when they're hanging off the side, the net force is only this because the gravitational force doesn't matter anymore. We have tension on this one. Of course, there's still M1G and the normal force. Those cancel out, and then M2G and tension here. So if the net force on the system is greater than it was before, right, because we don't have this, we're not fighting against this anymore, that means the acceleration is greater. Since the net force is greater. And that means that the difference between these must be greater. So tension must be smaller. That's the correct answer. So if the net force is greater, well, this is the same. They said for the same values of M1 and M2. So if the net force is greater, then that has to be less. You could also go back to here. You could actually solve for t if you wanted to, and show those two expressions and show that the t is less here. Either one of those will be fine. I kind of like this, just reasoning through it. And, oops, sorry, that was, how did I get? Maybe this was E. Somehow I got my labels off here, didn't I? Yeah, this is E. And D was the plotting of them. So this is F, and this is G. So in part G, the value determined for the acceleration due to gravity is lower in this one than the second one. Well, I mean, G should be the same. It's the same gravity. So why would it be lower in this experiment here? First thing that might come to mind is that since we have it up on a table now, we might think the table is close to frictionless, but if there is friction, what effect would that have? If friction is present, that means that the sum of all forces on the system is lower, which means there's a lower value for A, and a lower value for A, remember how we're doing this, this equation will look a little different now. The M1 will be gone there, right? But still A, if A is lower, then G is lower. So lower A would imply a lower value for G. So friction would be the culprit there. Worth noting here that I don't think, as best as I can understand, both their scoring guide and also just what they're looking for, that if you just say, oh, it's because of friction, that's not really enough. You have to justify why friction would make that experimental value of G lower.